So this video is about how a charge that's moving through a magnetic field can feel a force on it. Now, this phenomenon, this ability for a magnetic field to exert a force on a moving charge, forms the basis for most of our technology in the society. I guess the most obvious way it does that is through electric generation. This is essentially how generators work, where at the power plant they have these huge turbines that are essentially spinning magnets. They have coils of wire around them, and in that case, the magnetic field is the thing that's changing. But that changing magnetic field will exert a force on the charges that are like around the atoms in the wire itself. And by moving the charges around, they create current and supplying energy. That energy gets to our houses, and it runs almost everything, at this point. So personally, I think this is really, really cool. You have like these invisible fields, and you have these charges, and they can interact with each other without like anything physically touching. And I've always thought that was really neat. So first, before we get into this, some notation. So what we're going to find out soon is that we're going to need a way to represent a vector that's coming like straight out of the page towards you, like towards your face, or going back into the page, like towards the table. And there's a notation that we use for that. So when we think about a vector, remember we use these arrows, right? So if you imagine an arrow, instead of just an arrow, imagine like a bow and arrow, and it'll have an arrowhead on one end, and then it'll have the feathers on the other end, which is called the fletching. And so if you were to turn this arrow around towards you, the front of the arrow, where this arrowhead is, it would just look like a point maybe, right? Because all you see is the arrowhead. And then the back of the arrow, if you go behind it, the back of the arrow, because of the fletching, the feathers, you'd see a cross, like there'd be a feather like all around here. You see a cross. And that's the notation we use to indicate vectors coming into and out of a page. So if a vector is coming out of the page towards your face, what we'll do is we'll put a little dot there. We usually put an arrow around it to make it more obvious. It's kind of hard to see dots sometimes. So if you see this, it's representing a vector coming out of the page at you. And then a vector traveling into the page, like into the table, would be an X with an arrow, or sorry, it's not. It's an X with a circle around it. Okay, and so these are ways that rather than having to stay in the plane of the paper, like in two dimensions, we can represent vectors coming out of the page or going into the page. And then finally, since we are going to be talking about magnetic fields, we've talked about what they look like last quarter. Now we're going to talk about their strength. And the strength of a magnetic field, there's actually two units we use. One is this unit, the Tesla, which is the SI unit. And another unit that you may hear sometimes is the Gauss. Okay, so those are the two units, but we're going to be using Tesla in this course. Okay, so what's this relationship between magnetic field and the force on a charge? The first thing that I want you guys to really, really keep in mind here is that a charge, just a stationary charge that's not moving relative to the field, is not going to feel a force. Okay, so it's not that any charge feels a force in a magnetic field, but the charge has to be moving. And then furthermore, if the charge is moving parallel to the field, it's not going to feel a force either. Okay, so it will only feel a force if it's moving perpendicular to the field, or if part of its velocity is perpendicular to the field. Now, I've really been kind of shielding you guys this year from trigonometry. But for this, you know what? I think I believe in you. I think you can do it. And I think you can handle an equation that has a little bit of trigonometry into it. So say that this is our magnetic field. These green lines are our magnetic field, and we have this little charge, traveling at this velocity in blue here, and there's an angle between this velocity and the magnetic field, this angle theta. And if we kind of break this vector up in a triangle, we'll see that part of it goes up that way, and then part of it is going out this way. This one right here, notice, if I would have drawn it better, you would have noticed it even more. But notice that this part is 90 degrees with respect to the field. Because this velocity has part of the field, this part of the velocity is perpendicular or normal to the field, if you're going to be really geeky about it. This will feel a force, right? Whereas if this velocity was just completely parallel or going the opposite direction from the field, it wouldn't feel a force. And so the equation that gives us the magnitude of the force, and we'll talk about direction on the next slide, but the magnitude of the force, I'm going to call this F sub B, B we use for magnetic field, will be the charge itself in coulombs times the velocity of the charge, this is in meters per second, so as it's moving through the field, times the strength of the field, and again, for various reasons, we use B as our symbol for magnetic field. So this is our magnetic field strength, and this will be in Tesla. Okay. And then to make sure that we only get the part that's perpendicular to the field, we'll take sine, this trigonometry sine theta. Okay, so if you think of like this is V, if you guys remember SOHCAHTOA, sine theta is always opposite, the side opposite over the hypotenuse. This is a nice 90-degree angle here. So V is our hypotenuse, and the side opposite is the part of the velocity that's perpendicular to the field. So if we rearrange this just a little bit, we get the side opposite is our hypotenuse times sine theta. Our hypotenuse, once again, is V sine theta. So that's where the V and the sine theta come from. So really, all I'm going to ask you guys to do with this is to plug in the numbers. Okay, I'm not going to do a bunch of trig stuff, but I know you guys have the sine button on your calculator. I know you can plug in, and I know you can solve for the sine of an angle. So this is the equation for it, and by doing that, it gives you a lot of power, right? You can actually calculate the force that a charge will feel as it's traveling through a magnetic field, which I think is very, very cool. Okay, now the direction's weird though. I did not sketch his hand. I could not sketch his hand. I stole this from cite it. I stole this, but this is how we determine the direction the direction of the force on the charge, and this is called the second right-hand rule. So first of all, you have to use your right hand for this. The left hand does not work. Okay, so the second right-hand rule, what you do is you orient your fingers in the direction of the magnetic field lines. Your thumb, it says direction of the current, so that's the direction that the positive charge, I'm going to note that here, positive charge. Okay, we define current direction as the direction of the positive charge, which means that if you have a negative charge traveling through a field, you point your thumb in the opposite direction from the negative charge, from the direction that the negative charge is traveling in. So that's a little nuance you guys got to keep in mind. So that's the direction of the positive charge. And then the direction your palm points is the direction of the force. And so if you kind of look at your hand, you'll say, okay, well, if the field's in the direction of my fingers, and you stick your thumb out, and the thumb is the direction that the charge is traveling in, then the force is coming out of your palm. It's like 90 degrees with respect to both the magnetic field and the velocity. Okay, so that's why we need that three-dimensional representation of the field, because if we have our velocity and our magnetic field in the plane of the paper, then our force is either going to be coming out or going into the paper. Okay, we'll practice using this in class, but I just wanted to show you guys so you guys can start thinking about it and get down your notes. Okay, so I have a couple problems for you using the equation that I just showed you and using the second right-hand rule, and I suggest at this point that you guys stop the video, try to work out this first problem for yourself, and on the next slide, which I'll get to in just a sec, you I'll show you guys what the answer is. So again, I strongly encourage you, just go ahead and pause the video right now and work out this problem before you start and look at the next slide. Okay, I got 3.3 Tesla. Okay, I checked that a couple times. If I'm wrong, I want you guys to tell me in class. I don't think I am, though. All right, problem 2, same deal. Except this time I'm not going to ask you guys to solve for a number. I'm going to ask you guys to tell me a direction. So the first thing is, what's the direction of the force on this 4.5, this N stands for nano, this 4.5 nanocoulomb charge as it's trailing through the field shown. Remember, these X's indicate the field's going down into the screen, towards the table, depending on how you're looking at this. And my velocity is going from left to right. This is the velocity of a positive charge. So determine that direction. Then, what would be the direction if this charge was negative? And to do this, you want to use that second right-hand rule. So again, pause the video, just jot down your answers to these 2 questions, and I'll show you the answers on the next slide. All right, so for A, you should have got toward the top of the screen or the page, and B, you should have gotten to the bottom in the opposite direction from the screen to the page. All right, so that's what I have for this video, guys. Again, in class, if you guys have any questions, please let me know, and we will do some more practice problems, and you guys are going to get really, really good at this.